Now we do this formula for AC motor. AC motor got the equation N equal to 120 FIB. The motor run at the synchronous speed. So NS is a synchronous speed. F is the frequency. Frequency unit hertz. Synchronous speed unit is RPM. P is the number of poles. The motor speed can be calculated by using this formula. NS equal to 120 F divided by P. In this case, NS is a synchronous speed. F is a frequency. P is a number of the pole. Also, we can write down the slip speed. When the synchronous speed happens and when the motor is running with load, there will be motor shaft rotation. There is a difference between the synchronous speed and the rotation motor load speed. So this is a difference is a slip speed. Then we can also calculate the percentage slip equal to NS minus NR divided by NS multiply 100. Those are the equations for this motor. Okay, so then we solve the one problem. A single phase 240 volt 50 Hz 4-pole motor run at the rated speed 425 RPM. We need to calculate the synchronous speed. So in this case, given the motor frequency 50 Hz and also the 4 poles. So that we calculate the synchronous speed. The synchronous speed equal to NS equal to 120 F divided by P. So 120 frequency 50, number of poles is 4. You got the 1500 RPM. Motor running at the 1500 RPM. Then we can calculate the slip speed. So slip speed is equal to slip speed equal to the NS minus NR. So NA is 1500, NR is 1425. So there will be 75 RPM. Slip speed is 75 RPM. Then percentage slip. So NS minus NR divided by NS into 100. So the 75 divided by 1500 multiply 100. So there will be the slip speed at 3%, 5%. We also calculate the rotor frequency. Rotor frequency slip multiply stator frequency. Stator frequency is supply frequency. We connect the 50 Hz supply so that there will be the stator frequency 50. Slip is in this case the 5% given, so you have to divide it by 100 and stator frequency 50 Hz. So then you got the thing is 25 Hz. Rotor frequency 25 Hz we got. So this is how we calculate the slip speed calculation of the motor. Okay, the next one. The single phase 240 volt 50 Hz capacitor start induction motor has a running winding which takes the full ampere at the 0.6 power factor at the start, while the starting winding capacitor takes 3 ampere at the 0.8 power factor. We have to calculate the phase angle of the current and the angle between them, and also the current taken by the motor. So here is a single phase motor. Single phase motor got the starting winding. Starting winding is there will be capacitor, capacitor. This is a running winding. So this is a capacitor start motor. Starting, this is run. So this is starting winding and running winding. So we can draw this current diagram. In this case, starting running winding take a 4 ampere positive power for the lagging. So this is a IR 4 ampere 0.6 power for the lagging. And also the starting winding take the 3 ampere 0.8 power for the lagging. So here is starting winding. 3 ampere 0.8 power for the leading. Okay, so 0.6 power for the lagging and 0.8 power for leading, and then we can plot the Venn diagram. In this case, our 0.6 power for the lagging is an angle theta 1 equal to cos inverse 0.6. So we got a 53.2 degree. Angle theta 2 equal to cos inverse 0.8, we got a 36.8 degree. So they are two angles of the starting and running one. So after we got the thing, we can draw the Venn diagram. So how we draw a Venn diagram? We plot here the horizontal voltage is it. And starting winding got the 3 ampere point power leading, so this is 3 ampere. So this is the angle 36.8 degree. So IS. Running winding got 4 ampere point 6 power lagging. So this is the 53.2 to IR 4 ampere. So this is the way we can plot. So here we say that will be the this is a I total can be calculated. So the I total can be calculated by this formula. IT equal to square root of IS square plus I run square plus 2IS I run multiply cos angle theta 1 plus theta 2. This angle. So that here you can calculate IS is a starting winding 3 square. Running winding is 4 square. 2 into 3 multiply 4. And the cos is a theta 1 plus theta 2. So theta 1 is 53.2. Theta 2 is 36.8. So cos 90 becomes 0. Therefore, that will be the 3 square plus 4 square. So you got the 5 ampere. Current is a 5 ampere we got. That will be current is 5 ampere. And also the voltage across a 35 microfarad capacitor. So this capacitor is a 35 microfarad. So that we can calculate AC. 1 by 2 by FC. So 1, 2 by 8 is 2 multiplied 3.14 multiplied 50 multiplied 35. So to change the farad, multiply 10 over 6. So that will be the 10 over 6 divided by 314 divided by 35. You got the 91 ohm. Then we calculate the voltage. So VC equal to I into AC. The current flow into the capacitor is 3 ampere. AC value is 91. So you got 273 volt. That will be answer. There is one universal motor. Series universal motor, this is for the series field, and here is armature. And here we got the supply voltage V. This is a universal motor. So 240 volt series universal motor, total wide armature impedance is 600 ohm. We need to calculate the current taken by motor is starting. So there will be the total resistance R total. So R total RSE plus RA. So this way, the value is a 600 ohm. 60 ohm. And we supply the voltage 240 volt. So we need to calculate starting current. So starting current is I starting. So V divided by R total. Voltage is 240. Total resistance is 60 because the 4 ampere. Starting current becomes the 4 ampere. Then we have to calculate the current taken by motor when the armature back EMF is 120 volt. This means that the motor also produces the back EMF EB. So motor produces the back EMF. In this case, the current can be, we write down the equation. V is equal to EB plus I into RT. That equation. Firstly, we think about the starting condition. There is a no back EMF. Therefore, the full voltage is 240 volt is across the motor. Therefore, the motor current equal to supply voltage divided by total resistance. Once the motor is PR'd, it produces the back EMF. So when the back EMF is produced, we write down the equation V equal to EV plus I multiply RT. The equations. So in this case, the supply voltage is 240 volt, back EMF 120. We don't know the I, total resistance is 60 ohm. Then we calculate the I equal to 240 minus 120 divided by 60. So you got a 2 ampere. Current taken is a 2 ampere. The next one is a motor take the rated current 1.5 ampere. Then we have to calculate the back EMF. In this case, we write down the equation V equal to EB plus I into RT. So V is a unchanged supply voltage. EB is a we don't know yet. Current is now 1.5 ampere. Armature total resistance is a 60 ohm. Here we can calculate, so that will be the EB equal to 240 minus 1.5 multiplied 60. So 240 minus 90. So here we got the 150 volt. But here F is 150 volt. And also that we can also calculate starting torque as the percentage of the rated torque. And this case, torque is proportional to the current square. In this case, I is proportional to the I square. So the rated torque it can be calculated. Rated torque is depending on the rated current. So rated current I rated is 1.5 ampere. Starting current I starting equal to 4 ampere. So that we can now write down T starting divided by T rated equal to I starting square divided by I rated square. So the starting current is 4 ampere 4 square divided by the rated current is 1.5 square. 4 square divided by 1.5 square. So we calculate 4 square divided by 1.5 divided by 1.5. So you got 7.11 percentage. 7.11. So the percentage can be calculated 7.11 multiplied by 100. So you got the 711 percentage. This means the starting current will be about the 7 times rated current. So this is the way that we calculate this universal series motor. The next one, a 240 volt series universal motor, constant torque, load at the rated load, current 7 ampere at the 4,000 RPM. Speed to be reduced to the 2500 RPM. So this means the voltage is at 240 volt. So rated current 7 ampere at 4000 RPM. I rated 7 ampere and rated 4000 RPM. So this starting condition. Is the speed to be reduced to 2500 RPM. So in this case now N2 is at 2500 RPM. We need to calculate the voltage required to constant speed proportional to voltage. In this case, speed proportional to voltage. So we have to calculate the voltage. How much voltage? So as the speed is at 7000 RPM, so the current is a 7 ampere and rated voltage 240 volt. And when you reduce the speed to 2500 RPM, what will be the voltage? So that we can write down the equation. V1 by V2 equal to N1 by N2. So V1 is 240 volt, V2 is unknown, N1 is 4000 RPM, N2 is 2500. So we multiply, so this is the V2 equal to 240 multiply 2500 divided by 4000. So that will be the 150 volt. Answer. And the value of series resistance required to draw the motor voltage to this value. So we have to calculate the series resistance. So in this case, we can write down the equation. Rated current is 7 ampere. So we need to reduce the series resistance. So that in this case, rated current is 7 ampere flowing. So that we can calculate. So this is as our induced voltage back EMF. So that V is equal to I R total plus EB. So V240 total current is 7. We don't know the RT plus EB is now reduced to 150. So that we calculate RT equal to 240 minus 150 divided by 7. So that 240 minus 150 divided by 7. So that will be 12.860. R total is 12.860 we got. Okay, the next one is the alternator. F1 speed, master 24 pole 50 Hz alternator in a hydroelectric power station to be driven. So that in this case, we can calculate this speed and that's need to be calculated. In this case, number of poles is at 24 and frequency is 50 Hz. So we calculate NS equal to 120 F divided by P. So 120 frequency 50, number of poles is 24. So by solving this one, there will be the 250 RPM. Another problem. How many poles require on a 25 Hz alternator running 375 RPM? In this case, N S is equal to 375 RPM, and frequency F is equal to 25 Hertz. We need to calculate the number of poles. So NS equal to 120 FIP. Then P equal to 120 F divided by NS. So the 120, frequency 50, number of speed is 375. So we can calculate, that will be the 8 pole. Another problem. If possible, design the 50 Hz alternator right at the 1200 RPM. So that we have to calculate NS, whether number of pole or not, 120 F divided by P. So the NS is 120, 120, and frequency 50 Hz, and number of pole can be calculated. So P equal to 120 into 50 divided by 1200. So that will be the 5 pole. This is impossible, because you can't run the 5 pole. All pole must be the even number, not odd number. So you can't run. Impossible. The next one, 3-star connected 50 Hz alternator to be used as emergency supply. Output line voltage 1 kV. Power voltage must be generated each phase. So the line voltage is a star connected. So that will be line voltage is 11 kV. We need to calculate phase voltage. So phase voltage equal to line voltage divided by √3. So 11 kV divided by 1.7321. So you got, that will be 5.6 kV. Next problem. 2-pole 50 Hz 3-phase star connected alternator has a winding constant 0.097. Flux per pole 81 milliweber, 361 64 turns in the winding. So we have to calculate speed of rotation, generator voltage, output line voltage. So that in this case, the generator voltage equation can be calculated. E phase equal to 4.44 5F. So this is for the number of turns and also the other constant, winding constant. So in this case, so that will be the voltage equation of the alternator. 5 flux, F the frequency, and A is speed. So in this case, 4.44, and this other constants are, and the frequency. The frequency is can be changed, but the 4.44 and the other constant and can be changed. And here is number of turns. Number of turns can be changed. So therefore, the EPH is equal to the 5Fn constant. The constant is combination of the 4.44 number of turns other constant, or combination. So that constant value will be provided. So this problem generates a 2-pole at 50 Hz and 0.97. 0.97 is a winding constant. And also we can calculate the flux per pole 81 milliweber. So in this case, number of times given, so that we can calculate EPH equal to 5F number of turns and the other constant. So firstly, we calculate the EPH. EPH is so firstly, in this case, we also need to calculate speed. So the flux is given. The flux is how much given? So 81 milliweber. 81 into 10 power minus 3. Frequency is 50 Hz. Number of time is 364 times. Number of times 364 times. One constant is 0.97. So by solving this one, we get got the voltage. That will be 6350. So that will be the 81 multiply 50 multiply 364 multiply 0.97. And also 4/44. So that will be 4.44 multiply 81 multiply 50 multiply 364 multiply 0.97 divided by 1000. So that will be 6350. So for the EVH is a 6350. So the E line equal to root 3 multiply 6350. So you got 11,000 volt. And also we can calculate speed and S equal to 120 FIP. So that in this case, N is also the number of Dunbar phase. So we better write down the TB. 4/445 FTB into KD, that equation. So the 120 FIP, so the 120 frequency is 50 divided by number of poles. So that will be 2 poles, that will be 3000 RPM. So this program generator phase voltage can be calculated 4/445 FTP into KD. In this case, the 4/4 is constant 5 plus P is frequency and also the TPS is number of time and N is speed. So TP number of time and KD winding constant. So this problem is given the flux is 81 millihenry, frequency 50 Hz, and number of time 364. Winding constant 0.97. So by solving this one, so we got a 6350. So for this is a phase voltage, to get a line voltage multiply by root 3. And machine speed equation is 120 F divided by P. So 150 frequency 50 divided by number of volt 2. So you got the 3000 RPM. So this is the way we calculate it. The next one, alternator is a terminal potential drop 415 volt. Deliver in the full load at unity power factor. We need to calculate the no load terminal potential drop voltage regulation 13%. So the generator voltage regulation. So that this is a no load voltage minus full load voltage divided by V full load multiplied by 100. So this is the generator percentage voltage regulation. No load voltage minus full load voltage divided by full load voltage multiplied by 100. This is the generator percentage voltage regulation. So this problem, percentage voltage regulation given the 13%. So in this case, this is VR, percentage VR equal to 13% given and terminal full load terminal voltage. So the V full load is 415 volt. We need to calculate the no load, V no load. How much? So therefore, the percentage voltage regulate 13, substitute here. No load is we don't know V and L. V full load we got 415. Divided V full load is 415 into 100. So therefore, we can calculate V no load equal to 13 multiplied 415 divided by 100 plus 415. So that will be the voltage is 468.95 volt. So this is the way we got. The next one, 3-phase 6,300 volt alternator supply. Currents are 2,200 ampere at the full load. We have to calculate the rated kVA output. So this means the V line voltage is equal to the 6,300 volt and current IFL is equal to 2,200 ampere. We have to calculate rated kVA. So there will be 3-phase alternator. Rated kVA equal to √3 EI. So that will be the 1.7321 voltage 6600 current 2200. So that to convert the kVA divided by the 1,000. So rated kVA couple. Also this one we can calculate. So that will be 1.7321 multiply 6600 multiply 2200. So we got the 25,25150. So that will 1, 2, 3, 4, 5. So that will be there 25.15 MVA. The voltage will be 25.15 MVA or 25150 kVA. So this is the rated power can calculate. And we also need to calculate the output power as 0.8 power factor lagging. So in this case, we can calculate the power equal to the in active power in 1 unit. So the so kVA or MVA multiplied with 0. Power factor. Now you got the MVA is 25.15 MVA multiplied power factor is 0.8. So that will be the what you call is 20.1 megawatt. This is the answer 20.1 megawatt. The next one. The alternator with the full load terminal potential drop 415 volt. Alternator full load terminal potential drop 415 volt. Terminal voltage increase to 499 volt on no load. We have to calculate percentage voltage regulation. So in this case, V full load is equal to 415. V no load is equal to the 499. We have to calculate percentage voltage regulation. So percentage voltage regulation equal to V no load minus V full load divided by V full load into 100. So V no load is 499. V full load is 415 and also divided by 415 into 100. So this is 499 minus 415. Divided by 415. So that will be 20.24%. Percentage voltage regulation is 20.24. Okay, the next one. The terminal voltage of 70 MVA 3-phase 50 Hz star connected alternator is 11.7 kV. Armature winding breadth factor is 0.956. Armature is 16 10 per phase. we have to calculate maximum flux per pole. So that, and also full load current. So in this case, we can calculate the frequency, 50 hertz. Alternator got the frequency 50 hertz, and terminal voltage VT. So this is a V line is equal to the 11/7 kV. And breadth vector K 0.956. And time per phase equal to 16 times. We have to calculate flux. So we write down the equation. E phase equal to 4.44 phi FTP into K. So in this case, E phase is 11.7 kilovolts, so divide by root 3 because star connection. So the 11.7 multiplied 10 power 3 divided by 1.7321 equal to 4.44 and the phi unknown, frequency 50 hertz, time per pole is at 16 and K is at 0.956. So we can calculate the phi. Phi equal to 11.7 into 10 power 3 divided by the 4.44 and 1.7321 divided by 50 divided by 16 divided by 0.956. Then we can calculate the flux. The flux can be calculated by this way. So the 11700 divided by 4.44 divided by 1.7321 divided by 50 divided by 16 divided by 0.956. So that will be plus our pole is 1.98 Weber. So this is plus. We also need to calculate the full load current rating. So this is IFL. So this is a MVA FL divided by VT. So root 3 VT. So the mega volt and now we got that 11.7 kilovolt. So the 70 MVA. 70 or this is 10 power 3 is kVA divided by 1.7321 and terminal voltage we also know the terminal voltage 11.7. So the 70 divided by 1.7321 divided by 11.7. So we got 3454 ampere. The current is 3454 ampere we got. The next one, the 70 MVA alternator efficiency 92%. Full load is a 0.8 power factor. You have to calculate power output. So that in this case, output power equal to rated kVA multiply power factor multiply efficiency. So rated kVA is we already know the rated kVA. So rated are MVA we already know. So the rated MVA 70s are MVA multiply power factor is 0.8. Efficiency is 92%. So multiply 0.92. Then we can calculate to 70 multiply 0.8 multiply 0.92. So that this This is the output power of the machine. So the machine here, this is the alternator. Here is engine. So engine output power can be calculated. So this is output power of engine. So the rated kVA on the machine divided by efficiency. So this is divide. So 60.86. So and megawatt. So that engine power is a 65 megawatt. So because of that engine output, efficiency 92%, and then we can got the machine output. So this machine output divided by efficiency 92%, then we can calculate the input power of the prime mover. So this is the input power of prime mover. Input power provided by prime mover. Input power provided by prime mover is 60.86 megawatt. Okay, this program. The 4-pole singular motor connected to CC has supply where to determine the speed of the motor. So that in this case, singular motor. So this is the 60 hertz PS4. So the NS can be calculated 120 F divided by P. So 120 frequency 16 number of pole 4. So we got 1800 RPM. 1800 RPM. So this is what the speed. And also 3-phase 450 volt singular motor take the current 75 ampere. A full load, normal excitation, while driving the 50 kilowatt load. We have to calculate input power to the motor. So that will be the 4 poles are 415 volt. So this is the motor here, synchronous motor, and this is the load. Synchronous motor and the load. So the load power is 50 kilowatt. Load got the 50 kilowatt power, and this one take the 75 ampere from the circuit. And here will be the body is the 415 volt. So this is the motor driving the load power by 50 kilowatt. So motor taking the 75 ampere from the 415 volt power supply. So this is the calculate. So this is 3-phase. So we have to calculate the input power. So another thing is a normal excitation. So input power is root 3 EI cos theta. This is the equation. But cos theta is 1 because of the normal excitation. Normal excitation, power factor is 1 for the singular motor. For the singular motor with normal excitation, power factor is 1. Therefore, we can now calculate the input power. 1 by 7321 multiplied by 4415, current is 75, and power factor is 1. Then we can calculate this one. So the 1.7321 multiplied 415 multiply 75. So that will be 53 911.6. So this will be the 53.911. This is watt. So kilowatt. 53.911 kilowatt. So this is the input power. Also, we have to calculate efficiency. So the efficiency output divided by input multiply 100. So the output power is we know the 50 kilowatt. Input power is 53.91 into 100. So that will be the 50 divided by 53.91. So that will be 92.7%. Efficiency 92.7%. Speed can also be calculated. Speed 120 FIB. 120. Now frequency is a 50 hertz. Number of pole is 4 poles. So this is 1500 RPM. Also, we can calculate the torque delivered to load at the normal excitation. So torque can be calculated. So in this case, Y equal to 2 pi NT by 60, that equation. So T equal to 1 multiplied by 60 divided by 2 pi N. And the speed. So the calculate here, the output power we already know is 50 kilowatt, 50 into 10 power 3. Multiply 60 divided by 2 into 3.14 and speed 1500. So we can calculate 50 multiplied by 1000 multiplied by 60 divided by 2 divided by 3.14 divided by 1500. So we got 318.3 Newton meter. So this is the torque. And the current taken if the excitation reduced until the power factor is 0.8 lagging. So this means that we have to calculate power factor 0.8 lagging. So that will be we have to calculate this current. So in this case, we input power is at the same. So the same input power because of this output is 50 kilowatt. So therefore we with this efficiency 92.7%, input power is 93.91 kilowatt. So the input power equal to root 3 EI cos theta. So input power is 93.53.91 into 10 power 3 equal to 1.7321. Voltage 415 volt, current unknown, and power factor is reduced to the 0.8. Then we calculate the I with 3.91 multiplied 10 power 3 divided by 1.7321 multiplied 415 multiplied 0.8. So 3.91 multiplied 1000 divided by 1.7321 divided by 415 divided by 0.8. So we got 93.7 ampere. So this is the way we calculated this problem.